In this video, we will be taking a look at section 1.2, which covers domain and range. The domain is going to be the set of possible input values to a function, and the range is going to be the set of possible output values to a function. Usually in math, when we're thinking domain and range, what should come to mind is domain is your x's, because x's are usually your input values. And when you think of range, you should think of y, because y is usually our output variable. One thing we're going to be working with a lot is inequalities, and we need to have different ways to represent them. So for example, if we have an inequality x is less than -2, we have set builder notation, which is squiggly bracket, our variable, a straight vertical line, and then we copy over the inequality. The way we read this out loud is the set of x such that x is less than -2. In interval notation, that's the one where we only look at the endpoints, this inequality is represented by -∞ to -2. If we wanted to look at x is greater than or equal to -2, our set builder notation would be the set of x such that x is greater than or equal to -2. In interval notation, that would be -2 to +∞. We get a square bracket on our -2 because x can be equal to -2. In the last example, x could not be equal to -2, so we used parentheses. Next up, we're looking at -2 is less than x, which is less than or equal to 4. Set builder notation, just as before, we have the set of x such that -2 is less than x, which is less than or equal to 4. This time, x is between -2 and +4, so that's what our interval notation shows. We cannot be equal to -2, so it gets parentheses, but we can be equal to 4, so we get the square brackets. The next few examples show the different ways we can be equal and can't be equal to points. Then we're looking at a case where x is less than -2 or x is greater than or equal to 4. Set builder notation, same as always, the set of x such that x is less than -2 or x is greater than or equal to 4. For our interval notation, because there is an or here, we are looking at two separate intervals. So we write the first one, union the second one, because remember in math, union means or. Finally, we have all real numbers. The set builder notation for this is the set of x such that x is an element of the real numbers. Sometimes you'll see this as the set of x such that, and it'll just say x is real. What that means in interval notation is -∞ to +∞. So any real number can be used. We're going to practice our different notations. So if we're given an inequality, we're going to see if we can put it in set builder notation and interval notation. If we're given in set builder notation, if we can take it to inequality and interval notation. And if we're given in interval notation, if we can take it to inequality and set builder. So first up, we have x is less than 6. For the set builder notation, we start with our squiggly bracket, the set of, our variable, x, vertical line, stands for such that, and then we copy our inequality. X is less than 6. If we're looking at our x is less than 6, that means we're going towards -∞, and our interval notation will be -∞ to +6. We get parentheses on the 6 because x cannot be equal to 6. Next up, we're given the set builder notation, the set of x such that x is less than or equal to 7 or x is greater than 13. Since set builder notation is done by using squiggly bracket, variable, vertical line, inequality, to get the inequality, I just need to copy this part after the vertical line. So x is less than or equal to 7 or x is greater than 13. This is a case where we have the or, so when I do my interval notation, I'm going to have two intervals with a union between them. So for x is less than or equal to 7, we will have negative infinity to 7. 7 gets a bracket because x can be equal to 7. Or gives us the union. If x is greater than 13, that tells us 13 to infinity. We get parentheses on the 13 because x cannot be equal to 13. Next up, we're looking at 0 is less than x, which is less than or equal to 1. So for our set builder, we'll have the set of x such that 0 is less than x, which is less than or equal to 1. So it's just a copy of the inequality notation. We're saying that x is between 0 and 1. So our interval notation will be 0 to 1. Parentheses on the 0 because we can't be equal to it. Bracket on the 1 because we can be equal to it. In fact, that interval notation looks really similar to the next one. So our inequality notation should look similar too. This time we're saying x is somewhere between -8 and -5. So we will have -8 is less than x. We can't be equal to because it's parentheses. This time we're going to have a bracket on the -5, so that'll be x is less than or equal to -5. For our set builder notation, we'll have the set of x such that -8 is less than x, which is less than or equal to -5. Cannot draw squiggly brackets. It's a thing. There we go. Finally, we're looking at negative infinity to 3 union 4 to infinity. This looks a lot like the second one we did. So we see this union, which means we're going to have an or. So we're going to have some interval union another interval. Negative infinity to 3 means that x is less than or equal to 3. Then we have our union, which stands for or. And then 4 to infinity would be x is greater than 4. So our set builder will be the set of x such that x is less than or equal to 3 or x is greater than 4. Being able to go between these different notations is incredibly important, so make sure you do know how to switch between them. Now that we know how to write domains and ranges, let's see if we can work with them. We're going to start by looking at a graph. It says to determine the domain and range from each graph below. I'm going to zoom in so we can see them a little bit better. We're going to pretend there are arrows on the end of these so that they continue on. So first up, we want to find the domain. When we think domain, we're thinking x values, so we want to know what x values does this graph touch. Well, it's going to the left forever, so that's towards negative infinity. Going along, going along, going along. We get to an open circle here. I know it's kind of hard to see, but there is an open circle at x equals 3. So we get to go until x equals 3, but then there's an open circle, so we get parentheses. There is no place on this graph where x equals 3. That's an open circle, meaning that point doesn't exist. But we do start again at x equals 4. So that means we jump, so we union to 4, and that goes up and to the right forever, so that's to infinity. We have a closed circle on the 4, so we get a bracket. So if we know that we are in the domain of this function, that means we are somewhere between negative infinity and 3, or between 4 and positive infinity, because those are the x values that this graph actually touches. For the range, we're going to think the same way, but instead of thinking in terms of x, we're going to think in terms of y. So we want to start by saying, what's the lowest y value we ever touch? We're going down forever, so we're going down to negative infinity. As we're coming up, we are able to touch everything until we get to the x-axis, because we have that open circle here at 3, 0. So we would be tempted to say that our range stops at 0, but wait, we have a point that has a y value of 0 right here. Then we continue up forever. So our range is actually negative infinity to positive infinity because we never stop having any y values. We get from negative infinity up to 0, and we stop at 0, but wait, we have a point where y equals 0, so we get to keep going, and we go up to positive infinity. On this next one, we'll see if we can find the domain and range of this guy. For our domain, we're thinking in terms of x values, so how far left and how far right. We go from -2 to +2. We have a parenthesis on our -2 because there's an open circle at -2. We get a closed bracket at +2 because we have a square bracket at +2 because there's a closed circle. For our range, we're thinking of our y values. The lowest we ever go is a y value of 0. We are going to use a bracket on that 0 because we don't see an open circle here. And if we don't see an open circle, we assume there is a point there. So since there is a point where y does equal 0, we get the square bracket. Our range goes up until 4 because that's the highest y value we get to. You may be tempted to do parentheses because you see the open circle here. But on this side, we have the closed circle, meaning that there is a point here that has a y value of 4. So we get to use the closed bracket there. So for finding domain and range using a graph, you're just going to look at the x values and the y values that they touch. Next up, we're going to see if we can find the domain algebraically. So if we're given an equation, we want to know what is the domain. When we're working with an equation, what the domain is really saying is what x values am I allowed to plug into this. So we're going to start by assuming the domain is all real numbers. We can plug in anything we want. Then we're going to restrict it from there. We are going to remove any values that create a value of 0 in the denominator of a fraction. We cannot divide by 0 ever. So if there is an x value out there that will make us divide by 0, we're going to take it out. We're going to remove any values that create a negative value under a radical of an even root. So if we have a square root or a fourth root or a sixth root, then we need to make sure that the radicand, the thing under the radical, doesn't go negative. Finally, we're going to remove any values that create a non-positive value in the argument of a logarithm. So logarithms have a base followed by an expression. That expression is called the argument. We need to make sure that thing is always positive. So those are our restrictions when we're trying to find the domain of a function. So here we have 3 functions, and we want to find the domain of them. First up, we have f of x is equal to 2x minus 6 over 3x plus 4. We start by assuming our domain is all real numbers, and then we have to check, do we have a fraction? Yes. If we have a fraction, we have to make sure we're never dividing by 0. So that means I need to make sure my denominator, 3x plus 4, does not equal 0. I can subtract the 4 over. So 3x is not equal to -4. Then I can divide both sides by 3, and I get x cannot be equal to -4/3. I now need to check, are there any even roots? So do I have a square root, or a fourth root, or a sixth root, or an eighth root? Do I have any radicals at all? No. So I don't have to worry about that one. The third one I need to check is, are there any logarithms? So I have to check the argument. Not in this one. So my domain is going to be all real numbers except x cannot equal -4/3. We typically write our domains in interval notation, so that will be -infinity to -4/3. But we can't use -4/3, so we use parentheses. Or -4/3 to positive infinity, again with parentheses on the -4/3 because we can't use it. Looking at the next one, we have g of x equals the square root of 9x minus 3. We don't have any fractions this time, so we jump to the fact that I see a square root here. When we have a square root, our radicand, the thing under the radical, has to be greater than or equal to 0. We can't do negatives. I can add the 3 over. 9x is greater than or equal to 3, and divide by 9. X is greater than or equal to 3/9, which reduces to 1/3. To say that x is greater than or equal to 1/3, I have square bracket 1/3 to infinity. In this last one, we have h of x is equal to x over the square root of x plus 2. First up, I see that there is a fraction, so I need to make sure I'm not going to divide by 0. So the square root of x plus 2, I have to make sure that's not equal to 0. Well, the square root of something is 0 if and only if the thing underneath is equal to 0. So I need to make sure that radicand, the x plus 2, is not equal to 0 itself. If x plus 2 is not equal to 0, then I can subtract the 2 over, and I get that x cannot be equal to a -2. So I checked the fraction. Now I need to see if there's something else. There's a square root this time. So I need to make sure the thing under the radical, the x plus 2, is always greater than or equal to 0. So I subtract the 2 over. I get that x has to be greater than or equal to -2. There are no logarithms, so these are my two restrictions. X must not be equal to -2, but also x has to be greater than or equal to -2. I need to make sure I listen to both of those restrictions. So how do I make it so x is not equal to 2, but x is greater than or equal to -2? Well, if it's greater than or equal to, but not equal to, I can combine those together, and x must be greater than -2. It can't be equal to, because that would make us divide by 0. So I need to write an interval notation that x is greater than -2, which would be -2 to positive infinity. Now that we've talked about domains a little bit, we can talk about piecewise functions. And piecewise functions are functions that have different pieces. So a piecewise function is a function in which the formula used depends on the domain the input lies in. We notate piecewise functions as follows. We have f of x is equal to formula 1 if the domain to use formula 1, so if x is in there. We're going to use the second formula if x is in the formula 2 domain. Formula 3 if x is in the formula 3 domain. You can have as many pieces as you want in these piecewise functions. This one's different than the PowerPoint I had originally posted, but I like this problem better. A job in a warehouse pays $10 per hour for the first 40 hours worked each week. If an employee works more than 40 hours, they are paid $16 per each hour above 40 for the week. Write a function relating the number of hours worked to the total weekly pay and graph the function. So let's use capital P as our function, and that will represent the pay we get. And let's use H to represent the number of hours worked. So our function is going to be P of H because our pay depends on how many hours were worked. We had two different cases here. We get $10 per hour if we work less than or equal to 40 hours. So if H is between 0 and 40, we get paid $10 per hour. So to figure out our total pay, we will take 10 times the number of hours that we've worked. If we work for more than 40 hours, we get $16 of additional pay per hour. Well, we know that the first 40 hours give us $400. Plus, we get $16 per additional hour. But I need to somehow tell this function that the first 40 hours don't count. I already have accounted for those. I need to only count the ones above 40. So if I take my hours worked and subtract 40, I'm going to multiply that by 16 to figure out how much of that overtime pay I get, and that will be added to my 400 original dollars from the first 40 hours. This formula is going to be true if our hours worked is greater than 40. Now we want to graph this thing. 10h, that kind of reminds me of the form y equals mx plus b. So p of h is like our y, 10h is like our mx. So this is just a linear function, meaning it's a line. So if I can find 2 points on this line, I'm going to be able to graph that. Well, if h is equal to 0, I'm going to get 0 pay. If you don't work, you don't get paid. If I work for 40 hours, I'm going to get $400 pay. So 40 hours, $400, that's right here. Because it's linear, I can play connect the dots. This second function looks a little bit more complicated. We have 14 plus 16 times h minus 40. If I take a look at that function a little bit closer, 400 plus 16 times h minus 40, I can distribute through the parentheses. 400 plus 16h minus 640, that's 16h minus 240. That's in y equals mx plus b form as well. I only use this formula if h is greater than 40. So I need to find 2 points on this graph and see if I can make a line out of that one as well. So let's try plugging in h equals 50 and h equals 60. If I plug in 50, then 50 minus 40 is 10. 10 times 16 is 160. 160 plus 400 is 560. And then if I plug in 60, 60 minus 40 is 20. 20 times 16 is 320. 320 plus 400 is 720. So these are going to be 2 points on the second part of my graph. 50, 560 will be about here-ish. And 60, 720 will be about here-ish. This part of the graph goes as long as h is greater than 40. So I get really, really, really close to h equals 40. I can plug in h equals 40, and whatever I get when I do that, I'm going to have an open circle for this part of the graph. If I do plug in 40, 40 minus 40 is 0. 0 times 16 is 0, plus 400 is 400. So this point 40, 400 gets an open circle, but it's already a closed circle from the first part. So that's what our graph's going to look like. Yes, there is a limit to how many number of hours you can work in a week, but this gives us a really good idea of what's going on. So we get paid $10 per hour, and then it gets a little bit steeper because we get $16 per hour. I wanted to show you this example because this is somewhat realistic. There are many companies out there that will pay you time and a half, so meaning 1.5 times your pay, if you work overtime. This one's really close to that. If it were $15 an hour for overtime, then it would be time and a half. So this shows you the formula that's used to figure out your pay if that's the case. Now that we've seen a really applicable example, let's see if we can track this back into kind of the bare basics of it. Given the function f of x equals negative 2x if x is less than negative 2, x plus 4 if x is between negative 2 and positive 2, and 6 if x is greater than or equal to, we're going to evaluate f at a bunch of different points and then graph the function. So let's start with f of negative 5. So they want us to use x equals -5. I need to figure out which formula to use. -5 is less than -2, so I'm going to use this first formula, -2x. So I'm going to take -2 times my x value of -5. That gives me a +10. Next up, I want to evaluate f of -2. If x is equal to -2, then I'm in this middle situation. I'm going to use x plus 4. -2 plus 4 is a +2. F of 0, that puts us in the middle case again because we're between -2 and +2. If I plug in 0, I get 0 plus 4, which is 4. If I evaluate f of 2, then x is equal to 2. That puts us in this bottom case, which gives us 6. Then f of 3, again in the bottom case, we get 6. Finally, we want to graph the function. I'm going to graph this function in 3 different colors because it's going to help me visualize what's really going on. So I'm going to start with f of x equals -2x. Using y equals mx plus b, I know I can start at my y-intercept, the plus b. There isn't a plus b here, so b is 0. So I know that's where I'm going to start. My slope is -2, so I can go down 2 over 1. That gives me another point on this graph. And it's a line, so I just play connect the dots. And our graph looks something like this. The problem is this formula is only true if x is less than -2. So to the left of -2. This part doesn't even exist. And x is not allowed to be -2. It has to be less than -2. So we get an open circle at -2. Let's try this middle section, x plus 4. We started our y-intercept 4. Our m value is 1, so up 1 over 1. That's what this part of the graph looks like. But this is only true if x is between -2 and +2. So the stuff beyond -2 and beyond +2, those don't exist. On the -2 side, x can be equal to it, so we get a closed circle. On the +2 side, x cannot be equal to that, so we get an open circle. Finally, we have this last section, f of x equals 6. That's just like y equals 6. That's a horizontal line. So as long as x is greater than or equal to 2, our y value is 6. And this purple doesn't want to work. Let's try dark blue and just see if it works. But x is allowed to be equal to -2. So I need a closed circle where x equals -2, the y value is 6. So it just fills in that circle. When you're doing this on MyOpenMath, please draw it by hand first so you know what your graph is going to look like before you type it in. If you don't, you will make many mistakes and you're going to have to go back and fix it. So be sure to try these ones on paper before you do them online.